Hello everyone, my name is Yanjie. It's great to be here. Today I will give a talk on behalf of Peichen titled Revealing Floating Point Accumulation Orders in Software-Hardware Implementations. This is a joint work with Yang, Jilong from Microsoft Research. Let's look at an example where an LLM service gives different outputs for the same prompt. The prompt is generate a short excerpt of news about a journey to Mars. Even though the configuration uses a constant speed and temperature, the outputs are still not guaranteed to be identical. We could see this is a two-core response. We will explain why on the next slide. Why is reproducibility not guaranteed? Let's look at this figure. An LLM service performs intensive matrix computations at the software layer and runs on servers with accelerators, for example, the GPU. Each request may be routed to different software or hardware environments for load balancing. So we could maybe see different results for the same request. Software level optimization, for example, the dynamic batching also could affect the results. Numerical inconsistency is very prevalent. First, different results across hardware and software. We will see many different settings. For example, deploy the same model on CPU or versus GPU on different GPU specs. For example, A100 versus H100. In our investigation, searching for inconsistent results in PyTorch issues on GitHub reveals a large number of related reports, because we could see maybe more than 100 results. Additionally, our prior empirical study also observed a noticeable amount of output inconsistency issues over the LLM training systems. These issues can be highly disruptive for the developers and are often very difficult to debug because the kernel, maybe the operator are disclosed, and we can't debug this through debugger or through the tracing tools. The core problem is the accumulation order. We observe this. As we can see, various factors can contribute to output inconsistencies. As a core, the root cause is often floating point accumulation operations orders. The accumulation operations contain many types. For example, the sum, dot product, matrix multiplication. They have many varying accumulation orders in software and hardware implementations. This is an example in half-precision accumulation. Due to the floating point accumulation operations can have is not associative. These differences in accumulation order lead to small numerical variations, which can propagate and cause divergent outputs. This example shows how the order of addition affects the final results. If we turn the accumulation order different, they have one difference. So we think improving the reproducibility of emerging computation is very important. First, the numerical reproducibility is very common in emerging computations. For example, the deep learning, the scientific computing, and the database management. Second, the lack of numerical reproducibility is deemed risky and disqualified, especially in banking or the aerospace. Because the minor inconsistency in data are unacceptable. Finally, ensuring reproducibility boosts development efficiency and debugging productivity. For example, if we want to deploy LLM on the N series GPU, but later I got some A series GPU, I deploy the same LLM, they produce different outputs. We have no idea and spend lots of time to debug the root cause. However, determining the accumulation order of computational workload is very challenging. First, the rapid evolution of hardware and software stacks. The accumulation operator has diverse implementations. Second, the accumulation orders are rarely disclosed. For example, the N-series GPU is disclosed for the implementations. This hindering the reproducible accumulation order development. Third, the huge search space for revealing the computation orders, because we could brute force to construct all the accumulation order trees, but that is not acceptable when the data element size is very large. In this work, we propose FPRev, a diagnostic tool to help developers identify how accumulation operators are implemented, enabling reproducible software and facilitating the verification of implementation equivalence. For an implementation of an accumulation-based operation, we aim to design a diagnostic tool to reveal its accumulation order. In this figure shows our approach. The input of our tool is the implementation of the operator, and the output is accumulation order. On the right side is a summation tree for this operator. Our algorithm can determine the accumulation order from the numerical results of the tested implementation for specially designed testing inputs. We use an uninstructive approach to do the testing and construct all the accumulation orders. Let's see an example for the different accumulation orders. We observe discrepancies of NumPy in accumulation order for dot product, matrix vector multiplication, and matrix multiplication operations in single precision. For example, the figure shows the accumulation orders of NumPy 8 times 8 matrix vector multiplication on different CPUs. We know that CPU1 and CPU2 with 24 V cores, the 8 products of each output element are accumulated using two-way summation on the left side. Whereas on CPU3, which has more cores than CPU1 and CPU2, the products are accumulated sequentially. That is very different. This example shows the accumulation orders of hard precision matrix multiplication in PyTorch, which uses the cuBLAS backend, running on different GPUs. As in the previous cases, this accumulation order may vary across GPU models. This is very common and very important in deep learning workloads. So we propose the FPRev. Before we see our approach, how does our work works? FPRev is based on the phenomenon of floating point swapping. This is a phenomenon in floating point arithmetic is very common, where adding a small number to a much larger number results in the smallest value being effectively ignored due to the limited precision. This property is very important for us to reconstruct this accumulation order. For example, 2 to the power of 100 plus 2 to the power of 0 equals 2 to the power of 100. This loss of precision is due to how floating point numbers are aligned and rounded. The small number does not change any significant bits of the large number, so it gets swamped. To revealing the order of a floating point, we place m and negative m. M is a very large number at different positions as special inputs. We could observe it as a test case, and then analyze the output to infer the accumulation order between m and negative m, which allows us to deduce the overall accumulation order. Later, I will give a dynamic example for this, how it works. So let's see this example. First, we will construct the test case. Next, we will, based on the outputs of the test case, to construct the accumulation order summation tree. Let me give an example of how FPRev works. Subtree rotated at the neutralization of m, and negative m has 2 leaf nodes. In this example, m and negative m can cancel each other out to 0 as a node labeled neutralized because they are opposite. In this table, we using I and J to denote the index of M and the negative M. In the input, we know that the operation M plus negative M corresponds to the lowest common ancestor of node I and J in the summation tree. And the number of leaf nodes under the LCA equals to the n minus the summation output. Based on this finding, our approach enumerates I and J corrects the output for the corresponding input and infers the size of subtree routed and as the LCA node I and J. Let's move to the next step. In the next step, M as the index 0 and negative M as the index 2 cancel each other out to 0 at the node labeled neutralized. The number of the leaf nodes under LCA equals 4 minus the summation output, which is 4. The computation example is similar to the previous one. We will enumerate many combinations for this. So let's skip it. In the next step, let's see the final step. M at the index 2 and negative M at index 4 cancel each other out to 0 as a node labeled neutralized. This is very low level nodes as this tree. Is very near the final results. The number of the leaf nodes under LCA equals 6 minus the summation output, which is 2. Okay, let me summarize the idea of FPRev. If you are interested in the details, please see our papers. Let's start with the baseline. We begin with the naive thought, a brute force solution to construct all summation trees for specific number of leaf nodes. The summation tree is a binary tree. We will build all the combinations. So the time complexity is very huge. As you can see, where the T of n represents the time it takes to call the operation we are testing. Different operation will have different time. Next, as you can see, this quickly becomes intractable for larger n for the brute force approach. To improve this, we introduce our first optimization, basic FPRev. In this basic FPRev, we sort elements by n minus output, and then build the summation tree bottom up. This construction uses the disjoint set data structure, which efficiently help us merge subtrees and manage connectivity. With this approach, we reduce the time complexity to the big O of n squared times T of n, which is a significant improvement over the brute force baseline. Then we make further improvements. We could observe this hint in the example because we may see many duplication construction steps. Then we prune all the duplication steps. Then we make further improvements and we reduce the redundant computation. The final time complexity is the lower bound of the omega of n times T of n. Finally, we also add support for matrix accelerators, allowing us to apply these techniques efficiently in modern hardware settings. Okay, let's see how it works to construct the accumulation order for the summation tree. To generate the summation tree, we start by initializing the tree with 8 disjoint nodes labeled 0 to 7. Then, examining the smallest value in n minus output, we have n minus output equals 2 for I equals 0 and j equals 1. This implies the subtree rooted at the LCA of node 0 and 1 should have 2 leaf nodes. Since the summation tree is a full binary tree, node 1 and node 0 and node 1 are exactly the 2 children of the root of this subtree. For I and j equals 2 and 3, similarly, we can construct the subtree containing node 2 and 3. So computation example is similar to the previous one, so we could let's quick skip it. Finally, in the similar way, the next smallest unexamined value in n minus output is 8 for I and j equals 0 and 6, which implies that the subtree rooted at the LCA of node 0 and 6 should have 8 leaf nodes. Since node 0 and 6 are currently in two different subtrees, one has 6 leaf nodes and the other has 2, we should merge the two subtrees after we add the parent node of the current roots of the two subtrees and add the corresponding edges. The entire summation tree is generated. Let's now move on the experimental setup. We aim to evaluate the efficiency of FPRev across different dimensions. First, we asked how efficient is FPRev when applied to different numerical libraries. We evaluate it on NumPy, PyTorch, and JAX. Second, we examine how it performs across different types of operations, including dot product, matrix vector multiplication, and matrix multiplication. Third, we investigate how FPRev performs on different hardware, especially on Intel CPUs and NVIDIA GPUs. As for metrics, we measure the execution time, the workload time. We compare 3 algorithms in our evaluation. Naive solve is a brute force search baseline. Basic FPRev, this version solves inputs by n minus output and constructs the computation tree. FPRev, the optimized version, which promotes redundant search. Let's see the first result. The vertical axis represents execution time, and the horizontal axis represents the number of summons that the tree's leaf nodes, n. We test the single precision summation function in 3 libraries. The red curves indicate that the execution time of naive solve grows exponentially as n grows. The green and blue lines show that the execution time of basic FPRev and FPRev grows polynomially. The different slopes also demonstrate the execution time of basic FPRev is longer than that of FPRev and increases more rapidly as n increases. This trend suggests that scalability of basic FPRev is much better than the baseline. We also test applying basic FPRev and FPRev to the single precision dot product, matrix vector multiplication, and matrix multiplication functions in NumPy, and other results show similar conclusion. We also test the single precision matrix multiplication in PyTorch and different CPUs and GPUs. The result shows a similar conclusion. The result demonstrates consistent improvements in the runtime of FPRev compared to basic FPRev. Okay, in summary, we have several main contributions. First, the design and the development of FPRev. Second, empirical analysis and the evaluation of popular implementations. Third, we propose algorithmic innovation. Last, we also open source this tool. Okay, thank you for your attention. If you are interested, feel free to contact Peichen. Thank you.